Good afternoon. Good afternoon, everyone. Welcome to this webinar on machine learning for CAE. So my name is Melissa. I'm your host for today, and Koen will introduce himself in a moment. So just some house rules, so to say. If you have any questions, on the right side of your screen, you will have a panel where you can ask questions, and then Koen will answer them at the end or afterwards if we're running out of time. If there's a lot of questions. Recording of this will afterwards also be scheduled. So a brief introduction for people who do not know us or in Summa yet. We're from Summa, the official reseller business partner of Hexagon for the Benelux. And so Hexagon has a broad portfolio of many software applications, but also metrology applications. But we are focusing on the computer-aided engineering section. And so on the screen, you can see a few software solutions that we have. So anything ranging from standard FEA to CFD, acoustics, structures, materials, system dynamics, as much as you could want as an engineer. And so how does machine learning tie into that? Well, of course, it's kind of become kind of a hype topic, and that's also the reason why we're doing this webinar, because you can basically see and hear it every day all around you. Everything is about machine learning these days. But what can you practically as an engineer do with it? And that's what Koen is going to show you today. So, Koen?
Yeah, nice segue. Yeah, cool. Yeah, demystifying machine learning in CE. It's not really a secret, I would say. It's a bit of a hype. We have ChatGPT rolling around. We have other things flying around in the news outlet, and frankly, they paint quite a stark picture to what we as engineers would like to see. Quite a lot of hype, got a lot of things that get the clicks and the views, so to say. And today I want to basically just have a look through it, have a pragmatic view on it, have a discussion on it, see how we can apply this, see how we maybe want to use it later on, and then show some examples, and hopefully with that the viewer has a better view at the end of this session on what machine learning can do, how you apply it, and etc. So, yeah. I also find this funny jokes like to see on the internet, but like this is the stuff you see get thrown around on LinkedIn. I hate to use the term influencer, but you see this stuff a lot flying around on like quite popular pages beneath stuff like ChatGPT and like AI stuff thrown around, black box, it's going to take my job, whatever. We're going to look beyond this, and we're going to do this in a method that I consider just really the best way of approaching this, which is with pragmatic questions like what's machine learning, what can we do with this, and more importantly, how do we apply this actually in the CE setting? Because examples really, I think, will drive the point home of what you can do with this, and this is something relatable to us. Like a ChatGPT is something which is completely just not relatable to us. It's also not really something we can use, frankly. Well, just writing text or maybe send some sales emails. But as an engineer, we don't really have a place for that. So I wanted to really dive a bit deeper into how we as engineers can use this. So the first question: what's machine learning? It's the epitome of what I would consider machine learning is that we make some type of model that we have trained with historical data. And what I mean by historical data, I mean data that we have somehow gotten from experiments, for example, or we have gotten from simulations. Now we are in the simulation world really with our software, with our application. So most of the time, this historical data is what we gather from simulations. Now, important to know is that machine learning is a subset to artificial intelligence. So, although artificial intelligence can be more than machine learning in itself is an AI. It's in the AI field, and so it gets used up a lot. It gets mixed up a lot, and yeah. So if we think of some general applications, I read the reference ChatGPT. This is like a very like focal thing that came out, I think, in the last few months, and it's the most famous one at the moment. Some other ones are like CD Cortana, Google Lens for to get your to order a pizza on a Sunday afternoon, for example, like you would use that. But actually getting the speech recognition and linking that data to actually some words and some things to get a result from that. All that data is actually trained models, because it's all open-end when you ask something, and it needs to understand what's going on and what to hang to that. So that's like a typical machine learning example. But I'm again veering off into something that we don't essentially really relate to. So let's compare machine learning to something we're a bit more familiar with, like FEM or the CFD, and see how in the fundamentals the difference, like how the solvers handle these things differently. This will be the most technical stuff you'll see in this meeting, so don't worry, we will not be like dissecting neural networks, or we'll doing some interpolation methods. So if you look at this from something we understand, like a CFD or a FEM solver, we know basically the results with the given boundaries. In other words, the thing we're trying to solve is deterministic. If you gave it the same boundary conditions, it will give you the same result. Of course, accounting for computational efficiencies around of errors, etc. You'll get, like we could consider that you get the same result every time. If you relate this to this graph you see down here, we always get the red graph because we're integrating something. If it's in a transient simulation, for example, we're always integrating something in time. So what we're solving with the simulation is essentially this big red line here. What we're doing with machine learning is that we don't have this red line, and we are interested in getting this red line, but then with the historical data I referred to earlier. So what we're going to do really is we're going to train some type of model that will represent this red line using the blue dots we have over here. And the idea is that this red line is then a lower order formulation for it. So what I mean by that is that instead of a simulation taking a day, we can now run like 1,000 iterations in less than a minute, for example. So the idea for machine learning is that we quote unquote learn a formulation for the red line. And it's this other way of thinking that we should keep in mind for the remaining slides I will show you, because how much data you give it, what algorithm you select, and eventually also what type of data. So it can be, for example, just numerical scalar values, but it can also be like photographic input data, or there are a lot of different things. But it's important to know that we are basically trying to replicate the FEM or CFDs and all the intrinsic details you get by modeling these PDEs with data, and then using a lower order model then eventually to emulate basically the higher order systems. We are in a subset of supervised machine learning. What this eventually means is that we are using labeled data, and this example here is pretty straightforward because we have an airplane and we put some data below it. So we have an F-14, for example, over here, and we gave it the text string F-14. What we can do with this is we can put any data below here. So if we know that this airplane, for example, is very fast or it looks very good, then we can say that it looks good, and this one, for example, doesn't. And that's how we can also train models. So what we are essentially doing machine learning is we're putting some sort of context that these algorithms can find, and we are putting our own interpretations of it on it. And the supervised portion of that is that we already gave it the context of the system. If we're going to talk about, for example, unsupervised machine learning, which we don't really do, it's more of a data science thing, and it's not really applicable to us engineers. You would find that you will have there algorithms that will do the sorting for you. So if like data sets, where the n is like in millions of data, you're not going to label that by hand or by some type of automated scripting. It's most of the time more computationally efficient to do that with like machine learning algorithms. So to answer the question, what is machine learning? There are different answers for it, and it's a bit of a philosophical statement if you want to make it. But essentially, it's using some sort of training data set to train a model that will then predict very fast and very quickly, which is of lower order, but still captures the essentials that you should have seen in like your higher order model. So nice and all, but what can we do with it? I think that's like the more relevant question than what machine learning is. And if you look at this from a holistic viewpoint, we can do four things. We can do predictive modeling, so we can essentially get the trained model we gotten through our training data. We could have applied this, and then we can essentially look outside of our original design points. And I'll show this in the visual better in 2 slides further on. Classification, this is what I showed you earlier with the airplanes. So if I present if I show you that this is an F-14, we train a model with this, we give it new pictures, and the model will say, all right, on the top it's an F-14, on the bottom it's an F-16. That's what we call classification, or the model is classifying the photos for you. Now, this can be useful, for example, in some sort of quality assurance rule, or in some like niche cases like that in engineering. The other thing is sensitivity or parametric study. This is, as the name implies, really the study or the trying to determine what the influence of your parameters are on your system. I will show an example of this as well. And optimization, this is pretty straightforward. Like, this is using the machine learning model to essentially try different variations, and then depending on the cost function and how you have defined your optimization goals, it will get you the best answer. Now, why would you want to combine this with machine learning? Well, if we want to do this with some type of model that takes, for example, days to run, it's not really efficient to scope out your different combinations that the optimization algorithm thinks are good. You want something that predicts very quickly, and with that, it can really quickly assess if the cost function is good or not. And so that's why you want to couple optimization sometimes with a machine learning model, where you can very quickly run a lot of iterations to get to your optimized result. So let's dive a bit further into predictive modeling. It's pretty simple, but just to visualize this, let's consider a two-dimensional design space. So what we have here is we have 2 variables, x1, we have x2, and in this we have what we call a design space. And what you do normally to get a machine learning model is you do a design of experiment, or DOE, as I've referred to here. And with this DOE, you're basically testing your variable space, or your design space, what you see here. So let's assume in this instance that we trained our model with all the data we have here. So all the blue points you see here are data we know. These can be, like I said before, this can be empirical, or this can be from simulations. And what we can do now is, because our model is trained very well, we can now essentially try combinations that we have not tested before. So we can try these red points you see over here, and this is useful if you, for example, want to test new variations or new combinations you haven't thought of during the initial design phase, but did later on. Classification, like I said, it's the same example as what I showed you with the supervised machine learning. We can use labeled training data, so the photos, the aircraft, to really to quantify photos and use that data to do some automation in your in the QA process, where you want to take photos of something and then compare that for quality reasons, and then you can train, example, a data set that has bad photos. You can give it a data set that has good photos, in essence, that it will pass the tests, and that's a way on how you can apply this. This is a very interesting thing from a engineering point of view. Sensitivity analysis. This is something we always will do if you're working on a new design or some type of projects, because you know, based on your experience as an engineer, what the biggest influence for parameter are. This can be obtained through just sheer experience, or, for example, if you know the mathematical formulation of your problem, or have some experience with the physics behind it, which you normally should have. You kind of already know this, but let's imagine, for example, and we have seen this a lot actually, and it's what I've used this for a lot as well, is if we have a lot of variables and the system is very complex, so we're talking 20, 15 different parameters, and we know, based on our testing and our gut feeling, what is the biggest influence are, it's sometimes still very beneficial to just run 10 simulations, get that data in a machine learning tool, and then extract these graphs from it. Because what you can do with this is you can see the influence of your parameters both locally and globally. So you can see it on the total system, or local if you have for the local effects. And what you can do with this is you can essentially gain a lot of insight on what your parameters are. So you can quantify your parameter externality as well. For example, if you know, like, one parameter has a certain spread of upper and lower bounds, and you want to verify, like, you want to quantify how big of an influence that has on your final design, we can train a model with this like this, and then put that spread on that certain parameter, and it will predict basically your upper and your lower bound effects of it on your output. So this is a very powerful tool for engineers to use, especially when you're dealing with high order systems and systems that require a lot of optimization. Like I said, optimization as well, combine this with the sensitivity analysis, and you get into what I would consider the meat and butter for machine learning, and why you want to apply this as an engineer. What we did before is we now have insight in our parameters, and we now understand what we can disregard and what we can use as as our parameter set, for example. What we want to do with that then is we can use that knowledge to steer the optimization methods to get us answers to the optimum goal that as we defined it. And defining this can be literally as complex or as simple as you like. We can go from a maximum somewhere or a minima somewhere to multi-objectives across multiple data sets using constraints. So we can, for example, if we know that some parameters don't have effect on our outcome, or we want to fix it because that's optimal, for example, we can do that and apply that to the optimization method. And why this is so powerful is because it's using that machine learning model that we trained before to iterate very quickly. So instead of instead of having to get the data from simulations, we now have some sort of lower order model that still captures the essentials of the system, but that can be used to essentially just predict and iterate very quickly. And it's always fun to watch when you see the cost functions versus iterations just go down very quickly during the optimization process. So to recap, what can you do with machine learning? The main two takeaways I would say is we can optimize and we can study the parametric effects of your system, of your engineering problem, of whatever. Additionally, we can do qualification of photos. It lies a bit beyond what this process is I'm showing here, but it's more a thing we can apply to, for example, in the quality assurance process, where we know that we are looking at wafers, for example, in CPU production, and you can look at them visually to inspect them. And instead of having to do this by manual with an engineer, for example, we can train some model where it will pick out, for example, ones that are wrong and ones that are incorrect. And what you have to understand, of course, this is not 100% accurate, but it's way more efficient than to have some model pick this out for you and then present that to an engineer, instead of the engineer actually having to do this and having to look at it all for like 8 hours a day. It would get pretty boring actually if you have to do that, but that's a bit besides the conversation we're having here. So with that said, this is all fine and dandy, this is all pretty cool, but how do we actually apply this then in a CE setting? And I'll also go a bit beyond that, also a bit at some, like if you're a process engineer, for example, or some other things. It's really to show some applications, and this is just a look into what we can do with it, really, because if Melissa only gave me like 30 minutes to present, if I had more, I would be sitting here all afternoon presenting this.
I know I don't.
Yeah, there we go. So I'm not going to do that. So before we do that, I think it's important to highlight like how we get to this, because using machine learning algorithms is, especially when you look historically at this, pretty much the same as how the development of FEM and CFD solvers also went. You would get some type of university that will develop some type of open source or some sort of solver that they have customized and shared with them. And you will see that advanced engineers will use this to tweak to their likings. You will, for example, if we apply this in the machine learning world, we have packages from Google, for example, with TensorFlow, we have NumPy, we have PyTorch, we have Keras for a lot of really like advanced and up-to-date algorithms and methods of applying this. The downside to this, and this is a personal level thing, this is something you will see that people like to code their own stuff. We also have engineers that don't really like to do this and just like to get the answer from the algorithms, not really bother with all the coding and testing and doing that type of stuff. So for that reason, Hexagon has developed a tool, Odyssey, and we have two flavors of this, really. We have CAE. You will see the most of that later on during examples. This is a general purpose machine learning tool. So with this, we can load in CSV data, which is already a big step up from if you have to write your own code, because then you have to, the sorting of data is, I mean, like Excel is pretty standard across the industry for a lot of different things. So why not just put it in there, load in a CSV, and you can easily load that up in Odyssey. Odyssey AI is what we, it's a bit of a more advanced tool in that essence, that we can use classification for a lot of things. This is not limited to photos, hence the multi-data. We also, for example, can load in a step file, and then based on historical data we trained it, we can, for example, predict manufacturing time or ease of manufacturing or stuff like that. And really the goal and the main difference between something like Odyssey or coding stuff yourself in NumPy or in TensorFlow in Python is that you can just click away with Odyssey. The algorithms in there are sufficiently advanced enough to do things that we as engineers would like to do. I have not run into like errors with that. And doing something in Odyssey will take a few minutes because you load it in, you train your model, you will see your parametric influences, and from there you can just go on and go to your other tool. And I will show that a bit later on in our examples as well. So the main takeaway, what I would say here, is that you have some UI-based methods where you don't have to code stuff, and the training for you is essentially done because we have scripts in there that will try out all the different algorithms we have, and it will present you the best way. Well, if you work with some open source methods, you have to do that yourself, and you have to have some more fundamental knowledge of the algorithms and the methods you are trying to select. So you need it's a bit more of an advanced option. Of course, it has more advanced features, but that's a trade-off that's up to the user. So let's, before I show I will trust me, they're coming. But the main three ways where we apply machine learning in our CAE workflows is in the parametric study. This is a great way, I would say, of getting an insight in your model and understanding the effects of parameters on the long term. This only takes 10 runs, and what I mean by runs is how many variations you need to do in your design space. So if you reference our design space earlier, for example, with X1, X2, you would need to, well, that's quite a simple example, but if we have like, well, let's say 10 parameters, you need 10 runs to vary a bit of those parameters, and you can already see which parameters have the biggest influence, and that's very useful for the engineer to understand. Now, if we go up a bit, let's say we do 100 runs, we get a model that can be used for optimization. What you get with this is your accuracy will, well, of course, it depends on what we're trying to get, if the system is nonlinear, etc. But generally, after 100 runs, we can use it for optimization. It will give you a parametric set that has about enough confidence to predict you like 85–90% in the right direction. So this is then a step up. Now, if we add another 0 to that, so let's say we do 1,000 runs, we get a model that will predict basically on the dollar. So you get a model that will predict basically ±2.5% from your real data, and we can use this to do robustness and classification analysis. And the cases here is what I talked about earlier, that if you, for example, know that when your design variance for this part is, let's say, a parabolic curve or something, you can apply that then to this model, and you can really see within greater detail like how your model will behave, what the results are, and you can use that for a bit of uncertainty quantification on your production variables, for example. So the main takeaway is that it's machine learning provides the insight into your model, and it saves a lot of time on iterating. It saves a lot of time on just having to try different combinations. While you have some method here that will tell you it's not going to be 100% accurate, right? Because we didn't train it for that, but that's not the point. We need to get something that will give you basically 80%, 90% there on the way. Important to note as well is that it's solver agnostic, so it doesn't really care if it's coming from like our tools or from some competitor or from empirical testing. We can also just straight up just combine empirical testing with simulation data. It doesn't really matter as long as you as the user understand the context behind it. That's the important thing. Enough said. Let's have a look at some examples. The first one I want to show is with our CFD Solver, because I've used this a lot. I am quite familiar with this, so hence the example. We let CFD generate the 3D mesh and the results according to that. So we used the results file from SCFlow, which are FPH files, to basically generate a 3D reduced order model of our system. We train this in Odyssey, and then using new condition parameters or using optimization, for example, we can then make predictions and see that result happen with the result files. So what we're using here as output, or as input, sorry, is the mesh really, because we're training nodes on a mesh level at this point, and then we're using it later to visualize our results, which is quite a powerful tool. So let's consider it's a pretty simple example for the reasons, of course, like I said, otherwise I would be sitting here for 3 hours. But the idea really is that in this case is that we have some type of chip. We have a heat load to it, we have a fin thickness, and we have an inlet velocity. So as you see here at the top, this is our simulation. It's a very simple PCB with a chip on it. And we have a cooling fan over here with fresh air getting pulled in from the side. So what we can vary in this design, and again, it's only free to show you the process really. We're gonna vary our inlet velocity. We're gonna vary the wattage generated by the heat source, which is below the cooling fin, and we can change the fin thickness. The design objective for this, let's say this study, was not to exceed 50 degrees Celsius on the top, so the interface between the cooling phase and the fin base. And the method for this, what we did is we trained a 3D flow field model. So like I said, with the results we had here before, we're going to train on the mesh level, we're going to train a model. And what we're going to do is we're going to apply a optimization goal that we may not exceed 50 degrees on the chip. So what we have as output essentially is the temperature for each node or element in our mesh for a CFD study. Now we did 20 simulations for this, and what we found already right away is what I referred to earlier. Our sensitivity of our parameters. We see that our inlet velocity, so the speed at which the air enters the case and therefore also cools the stuff, has a big influence on this. Reason for that is, well, it's obvious, right? More airflow means better cooling. And we found that the heat source doesn't really matter too much. We could vary this between 15 and 30 watt, but of course it had some influence, but it didn't really matter too much on how hot the chip got. Fin thickness had a secondary, or like it had a second effect, and although still significant, we could see that the inlet velocity was the biggest contributor to our thing. So what we did is we set the optimization goal, we let it iterate, and eventually what you will get, and this is just some random combination, but what you will get is you'll get a combination of parameters. So what we then can do is put this in our CFD simulation, validate what the model predicted, and then according to the boundary conditions and the models we gave it, we have now an optimized design, because this is according to the data we fed it, and if the data is of course fed correctly, then that's the constraints in which it must work. We now have an optimized design, and it's that process of getting insight into parameters. So your inlet velocity has the biggest influence, and it's positive. So that's something, heat source and your fin thickness is combined with the optimization where you'll get your parameters back, is one of the main ways you want to use the machine learning tool, really, because this is the bread and butter for it. Now, what we can do then later on is we can, and I hope it plays because this is a fun little movie. Yeah, there it goes. So what you will see here now is that these are the comparisons between our CFD simulation on the right and the 3D reduced order model that we created on the left. And this is directly related to the optimization. So we got this information, we got the corresponding parametric information, and then we can also validate it later on with a prediction, and then subsequently the validation as well. Now, why I'm showing you the CFD case is because this is built into our CFD solver. So you don't have to do a lot of data manipulation. You don't have to basically reinvent the wheel for the machine learning tool to work. We have a DOE-based method in our CFD application. And we can combine this then with the results files to essentially, with a few clicks, generate this model, let it optimize for you, and then in the end get the effect on parameters. So the idea is that you implement this in your, or that the idea from the developers outwards was that the implementation was as easy as possible. So you don't have to really do much, just click the buttons, let it run, and the system will generate the data and the input from it. We can also do this in some other tools, because the same thing is also integrated into our nonlinear solver, so Mark Mentat. This is even simpler actually, because what we do here is we can make our model completely parametric. And what I mean by this is that we can vary anything as long as we can get the scripting line for it. So we can change model parameters in the sense that your material model, for example, can be changed. You can change physical parameters. You can change geometric parameters. You can do a lot of things with it. And like I alluded to earlier, this is built into our software, and the goal for this really is to use this as a like a one-stop shop. So you do a bunch of simulations, you let it run overnight, you press post-process, you have the data ready, you load it in, you look at your data, and within 10 minutes you essentially understand the design constraints of your design and you know how to move forward with it. Now, if we apply this then a bit later on, like for example, an FEA design workflow, we can use let's say Apex, like this a general preprocessor. We can apply some things there, like such as defeaturing, cleaning up our CAD. We can then load that file into Mark, where we do our nonlinear FEA. We generate our FE model. We generate the training data. We let that run for depending on the complexity of the model, of course. Sometimes we can do it in an hour. Sometimes it takes a bit longer. And you come to the office the next morning and you have your data ready to go. You load it in an Odyssey. You see your parametric effects. You see what the biggest influence is. Comparatively, you press optimize. It might take, again, on the complexity, it might take a few seconds. It might take a minute for a bit. But then essentially you have a design point where you can work from. And this iteration time reduction is really why you want to use this in your workflow. Of course, some models are too big for this to be used. So that's an important thing to consider. If you're using a model that may take, I don't know, days or like a day or days to run, which is not really something that's out of the question if you're using CFD, especially that can go on for days. So for example, in that workflow, it wouldn't really make sense. But if you have an example, and of course they're all kept simple here for presentation 6. But if you have a model that you can run for, let's say, a weekend, or then you have all the data ready, you load it in, you train it, and you have your answers already. And that's where something like Odyssey really shines, or like where you want to use your machine learning tool for. So that's in a CAE workflow really the added value of Odyssey. It's design optimization, it's insight in your model, and it's also a bit of optimization because, or a bit of automation of doing a parametric design study. Because with this, you can just let it run in the background. It will vary the systems for you. All you have to do is define what you like to vary. So, like I mentioned before, this can be anything from geometric changes to physical model, solver settings to whatever really. And you let it run, you import it, you see your parametric influences, you optimize, and you're basically good to go. Of course, your design has to make sense, etc. And that's something that we'll get on during the training. But this ease of importing with CSV files with automatically running is really why we consider this such an added value for a design process flow like this in an FEA workload. Same for CFD, like I showed you earlier. Well, let's move away from that for a second. Let's have a look at what you can do with image classification. And this is, again, a simplified example, but this is something I alluded to earlier. We can essentially put any context or any data to the photos we have. So if you, for example, here we have a bunch of NACA standardized airfoils. We can give it lift coefficients and drag coefficients. And then if you want to show a new photo for it, for example, it will give you these values based on the training set back to you. This is a bit of a not really a useful example, so let's apply this to the QA thing I was talking about earlier. What we can do is we can have images of PCBs that were correct and incorrect, and we can then essentially train a model for us to automate this process for you. Like I said, I wouldn't want to be the engineer who sits 8 hours at this looking at it, trying to pick stuff out. Why not have some like image recognition model working on this, because it saves time both in just full on FTE hours, but also in just simply looking only at the ones that need attention. So and the more you train this, the better the system gets. So it's like this positive feedback loop where if you keep on training the model, if you keep on giving it more stuff, it will be it will get better. So this is a powerful application of machine learning. I would say we have seen this at customers as well, where this is basically, and I hate to say this, but like it reduces their time by like 50 or 60%. Like it's such an unquantifiable thing. But if you have some workflow like this is a standard, like a perfect application for it. This is a bit more of a conceptual one, but we also have seen this a lot, and that's the quality management of your product. So this is very applicable, for example, if you are a production engineer, and as production engineer, you can tweak certain variables, and you want to basically make the process as effective and as cheap as possible. Not cheap, but as cost efficient as possible. And what you have a lot of times is you have a wealth of data already ready, because if shop floor users most of the time log certain values like input parameters or things like that. And what you can do with that is you can load those in Odyssey again, or in some sort of machine learning application, and you can see what the effects are of the parameters. You can use that then to, for example, minimize or maximize some things, or what like your lowest allowable is for a for that model. And this is especially useful if you know what the spread will be, because if we're making something, it's never going to be an absolute value like we have in simulations. There's also going to be a bit of spread to your parameters, and quantifying that and understanding how much of a spread you can accept for your final design is well, it's very powerful if you're a process engineer, for example. Another thing where we have worked on is essentially the speeding up of shop floor processes. And what I mean by this is that normally if you have a skilled operator doing stuff, we're not going to replace them with machine learning. And I also see that a lot. It's not going to happen. But what you can do with this is that you can train some model that will use data to reduce the iteration time. So what you can have, for example, is if you need to like you need to calibrate the model, or you need to, based on customer specifications, need to have some certain system behavior, we can apply a machine learning model to this, because most of the time the process is repeatable and within a certain context. So what you can do then is you can ask the model, all right, I want to have this set of parameters and I want to have this goal. You press optimization tool, you let run for a bit, and it will give you a solution basically where you start from here, instead of having to be at higher up on the curve on the product configuration. So your iteration time is reduced again a lot with a model like what we can use in machine learning. So it's time saved. That's again a big factor. Oh, with that, I think I have put it right on the money where I should keep it. The main takeaways I want you guys to have from this is that machine learning is a hype, but it has some applications. It really is good for problem optimization. You get a better understanding of your parametric effects due to the way that we approach the data. And we can use predictive modeling to test unknowns and get a better understanding of your design, like I showed you with the FEA design load, with the CFD load or design process. So it adds insight and design optimization in your CAE workflow, which is the main goal really for the machine learning tools. It's a process that will save you time. It will save. It gives you more insight, saves you time, and yeah, that's like the main takeaway to get from this. And I also like to highlight that it's solver agnostic, so it doesn't care like what you're going to feed in it. So we also had questions. Well, if you're not using Hexagon products, can we still use then the machine learning applications you have? And the answer is yes, of course, because it's CSV data. It's not some proprietary like PDF or T16, for example, result file from Mark Mentat, or so it's solver agnostic, and we can use it on a lot of things. With that, I would like to really close this. We have an Odyssey workshop the 16th on the next month, where we dive a bit further into this, where I will show use cases. You will get hands-on with the software. I will show you how to apply this. We dive also a bit, of course, in machine learning theory behind it, because I find it interesting, and you probably do as well. And yeah, I think that's it for me. It saves time, you understand your parametric effects, and optimization on the machine learning model is very quick, very fast, and it saves you a lot of time there. So yeah.
Sounds really easy when you put it like that.
Yeah.
Good summary. Just for people that are still in the call, as Koen mentioned, and by the way, in the moment, you can leave your questions for Koen in the chat now, so we can answer them. But as Koen mentioned, we have a workshop next month, exactly a month, Thursday the 16th. And so there you can, if you would like to join, and Koen, if you can put on the next slide.
Sure. Oh, thanks. Yeah. Thanks for joining, everybody.
Next.
Of course.
Sure. Yeah, you can contact Koen if you would like to join this workshop. He has all the. It's going to be from 10 to 1. We'll take care of lunch, and it's at our office in Amsterdam Sphere. And just send Koen a message if you're interested.
Maybe to add to that as well is that if any people have some type of use case they have in mind, for example, just don't hesitate to send me a message. Like, I'm happy to discuss anything really, and it's I think it's important to have the conversation because there are some very nice applications for this. For this technology, and yeah, like I said, I've been using it for quite a long time now, quite a lot of experience in this, so happy to help with users who have questions in this. So, yeah.
Good. So I've got one question here. Can Odyssey also deal with multiple load cases and optimize to a solution? Which is the best overall?
Yeah, good question. Very good one. So load cases, yeah, it can work with that. And this is again some of the intrinsities of getting into the modeling phase. This is something I would like to maybe send me a message like this with some context to it, like if it's NDA covered or something like that. I'm happy to discuss about this because it really, the answer is yes, we can do it. And there are multiple ways of tackling this. So that's kind of the best answer I can give. We can do, the optimization can be across many data sets. So the global type, what I mentioned too, where it will look and try to find the best parameters between different results or load cases. We can also do global or local, where we apply this a bit more on a local level, so on a single load case, for example.
I hope that answers the question, and if not, then feel free to reach out again, of course.
Yeah, of course. Yep.
But of course, like the more complex it will get, the more time it will take, of course.
Yeah, but that's in general, it's something that's always case dependent. Yeah, and
that's always. Simulations software
yeah.
Engineers know that probably. And so what is needed for a good model is another question that's asked.
Sure, yeah. Let me actually have a slide for, I hope I can access this.
Oh, you have another slide, cool.
Well, good question, like what's required for it. We need 3 things really. We need repeatability. We need something that so we need something that can be processed and it will give you an answer every time. So what I mean by this is, for example, a simulation where you tweak some parameters and the simulation runs, it ends with a good answer. That's something that's repeatable. Same with testing, right? If we do some testing on some physical model and we get some empirical results from that, that's also something we can use. That's repeatable. We need something with the set of boundary conditions. So we need input parameters that are defined from the first. So we need an upper and a lower bound in that. And we need to repeat that across our repeatable system. And we need an output that captures that's like a design goal. So let's say, for example, we want an aircraft to fly at a certain speed, then drag, for example, can be a very good output because we want to minimize that. And this is very hyperbole, but to give an idea to the one who asked the question. So
hope that's clear. So yeah, some people asking about the recording. Of course, we'll share this with you guys. And then yeah, something about the algorithms. A couple of questions. Like, of course, engineers want to know these things.
We don't, and so 2 answers. First one is you don't need to know them, and the second one you can know them, but then apply them still in the essence that Odyssey or some tool like that will give you the answer for you. What I mean by this is if we load in our data, so our training data and our validation data, we can run certain automated scripts that will basically try all the different methods, and it will give you an answer that's either you need more data, or we recommend you to use this method, which will give you the best result. And we do that with fitting parameters such as, it's a bit too technical for this meeting probably, but like basically comparing areas underneath the curve or trying to look at the mean square error between prediction and the actual data. So.
Okay.
So just to harp on a bit more, it's automated in it, so you don't need to. That's why I said 2 answers. You don't really need to understand what's going on, but of course it's always good to know what's going on. So that's why 2 answers.
Another question is next month's event also going to be online. So this workshop next month is going to be a bit more interactive. So we're going to do it physically, not online. But of course, if you're not available or not able to join, please reach out to us, and we can always plan something separate if you're interested. I'm not sure who is asking this question. They haven't published a name, but in any case, feel free to reach out if you're interested. We can plan something via Teams separately. Right, Koen?
Yeah.
Okay. I think that's all it for like timing wise. So again, send Koen an email if you want to join the workshop, so we can deep dive more into machine learning together and what it can mean for you and your workflows and your simulations. And with that, I'd like to thank you all for joining, and hopefully see you soon. Thank you.